In this video, we're going to talk about the domain and range of a function, which are two very important sets associated with any function. To get a sense of what the domain and range are all about, let's try to think about a general function f from a set A to a set B, and consider its diagram. Right? So we'll begin by representing the sets A and B by two abstract blobs. Recall that, by definition, a function is a rule that's going to take elements from the set A and send them into elements of the set B. We can therefore think of elements of the set A as inputs of our function. And similarly, we can think of elements of the set B as the outputs of our function. So we feed in an element from A, and then our function will return to us an element or output from the set B. Let's now make things a bit more concrete and imagine that the set A contains exactly 4 elements, and that those 4 elements are just the numbers 1, 2, 3, and 4, and that the set B contains exactly 3 elements, and that those elements are the numbers 0, 1, and 2. Here now is an example of a function from A to B, and all the arrows are crisscrossing in various ways. We can tell at a glance that this really is the diagram of a function, because every input of the function, every element of the set A, is being associated with precisely one element of the set B. In fact, the numbers 1 and 3 are both being sent to 1, and the numbers 2 and 4 are both being sent to 0. It's actually possible to interpret this function in a nice way. This function is taking a number and returning its remainder upon division by 2. In any case, if we ask the question, what are the possible inputs of the function f, then we would have to say that the set of all possible inputs consists of the numbers 1, 2, 3, and 4, right? Those are the possible numbers that you can feed into the function, given our diagram. On the other hand, if we ask the question, what are the possible outputs of the function f, then we see that the values that the function f can take are precisely the numbers 0 and 1. In particular, the function does not take the value 2. So the set of all possible outputs of the function, as the inputs range across the numbers 1, 2, 3, and 4, consists of the set of numbers 0 and 1. This example leads us to a general definition. In general, we say that the domain of a function f is the set of all possible inputs of f. Likewise, we say that the range of a function f is the set of all possible outputs of f, or the set of all possible values that the function can take. So, returning to our example and armed with our new vocabulary, we would say that the domain of the function f depicted here is the set of numbers 1, 2, 3, and 4, and that the range of the function f is the set of numbers 0 and 1. Now, a function may be presented to us in the form of a picture or diagram, but we also know that if a function has inputs and outputs that are real numbers, it is often possible to present it via an algebraic formula. So let's think about how to find the domain and range of a function when that function is presented to us using a formula. As a first example, let's try to find the domain of the function f of x equals 3x squared. So the way this function works is that you can feed a real number x into it, that's the input, and then the output of the function will be that real number x squared and multiplied by 3. And to find the domain, or the set of all possible inputs, what we need to do is think about which real numbers x can be substituted into the expression 3x squared. And a bit of thought here shows that the answer is, well, all real numbers, right? Every single real number x can be squared and multiplied by 3. Therefore, we would say that the domain of this function is the set of all real numbers, or, using interval notation, the open interval from -infinity to positive infinity. How about the function f of x equals radical x? Let's think about the domain this time. What is the set of all real numbers x that can be fed into the expression radical x? Well, notice that it doesn't make sense to speak of the non-negative square root of a number x if that number x is negative, right? Because that cannot give us a real number output. So the only numbers that you can feed into this expression are the numbers x that are greater than or equal to 0, because otherwise the expression is not defined. Or to be more precise, otherwise the expression does not have real number values. Therefore, the domain of this function, using interval notation, is the interval from 0 to infinity, right, with a closed left endpoint, or simply all numbers x that are greater than or equal to 0. And let's take a look at the function f of x equals 1 over x next. What is the domain here? To answer that question, we simply need to observe that the expression 1 over x is well defined as long as x is not equal to 0, right? Because we can't divide by 0. Therefore, the domain of this function will be all real numbers except 0. Or, using interval notation, it will be the union of the interval from minus infinity to 0 and the open interval from 0 to positive infinity. Let's go through our examples again, and this time think about the range of the corresponding functions. So, beginning with the function 3x squared, we now have to think about the set of all possible values that the expression 3x squared can take. Notice that x squared can never be negative, although it can take on any non-negative value. This means that x squared, and equivalently 3x squared, will fall into the range from 0 to infinity. Let's think about the possible values of radical x next. By definition, radical x will always be greater than or equal to 0. And if you think about it a bit, you should realize that it can actually be any number that is greater than or equal to 0. Indeed, the square root of a number can be arbitrarily large. So the range here would also be the set of all numbers that are greater than or equal to 0. Finally, let's think about the possible values of the expression 1 over x. Here, it's not quite as clear as before, perhaps, but a bit of reasoning shows that 1 over x can first of all be positive or negative, in case x is positive or negative. And in fact, it can be arbitrarily large or arbitrarily close to 0. The one thing that 1 over x cannot be equal to is 0 itself. So the range of this function will actually coincide with its domain. It will also be all real numbers except 0. Let's conclude by thinking about a problem that's significantly more challenging. Let's try to find the domain of the function given by the rather complicated formula radical of 9 minus x squared plus 1 over x squared plus x minus 2. Let's begin by taking things one step at a time and breaking our function up into two additive pieces, the first of which is the radical of 9 minus x squared. Well, we know that as long as we're taking the radical or positive square root of a quantity, that quantity, which in our case is 9 minus x squared, must be greater than or equal to 0. And solving this inequality, we find that x squared must be less than or equal to 9, which in turn tells us that x is less than or equal to 3, and greater than or equal to negative 3. Or, writing the solution of this inequality using interval notation, we obtain the closed interval from minus 3 to 3. Let's take a look at the second additive term of our function next. We know that 1 over x squared plus x minus 2 will only be well defined if the denominator, that's x squared plus x minus 2, is not equal to 0. We can solve this condition by factoring. So the quadratic expression on the left-hand side factors as x minus 1 times x plus 2, and we need that to not be equal to 0. Well, we could see immediately that it is equal to 0 exactly when x is 1 or negative 2. And using interval notation, the set of all real numbers that are not equal to 1 or negative 2 can be expressed as a union of intervals. It'll be the open interval from minus infinity to negative 2, union the open interval from negative 2 to 1, union the open interval from 1 to infinity. Looks like a somewhat complicated set of real numbers, but it's just a set of real numbers that don't contain 1 and negative 2. So what's the domain of our function? Well, in order for a number x to belong to the domain of f, it must be the case that it belongs to the closed interval from negative 3 to 3, and that it does not equal 1 or negative 2. So the domain of this function will be the intersection of the two sets of real numbers that we found by examining the two additive terms of the function. Taking the intersection, we therefore see that the domain of f is the union of three separate intervals: the half-open interval from negative 3 to 2, the open interval from negative 2 to 1, and the half-open interval from 1 to 3. Again, that might look kind of complicated, but it's just a way to describe all of the real numbers that are in the closed interval from minus 3 to 3 and that do not equal negative 2 or 1.